Hello everyone, welcome to this presentation. My name is Sadek Surjani. I'm a lecturer at the School of Computing, Newcastle University. This presentation was given last week on November 9, 2020 as part of the verification seminar at CNRS Research Institute on the Foundations of Computer Science. In this presentation, I'm going to talk about formal verification of stochastic systems using Markov chains and the dynamic Bayesian networks. So this slide shows the high-level goal of my research. In general, in computer science, we usually work with models that have a discrete state space. For example, finite state machines, timed automata, Petri nets, and so on. Even in the stochastic setting, we have Markov chains and Markov decision processes with finite number of or countable number of state space. If we look at the class of specifications studied over these models, we have rich classes of specifications, for example, linear temporal logic or continuous stochastic logic and so on. And we have also lots of concepts and techniques on how to check these complex specifications on such models. Now, if we look at controls theory, the nature of the model itself is complicated. For example, we may have a differential equation. It could be nonlinear with a continuous or hybrid state space. We may even have noise as Brownian motions or other types of noise affecting the behavior of the system. But the class of specifications studied in control theory is relatively simple. For example, safety or reachability. So in my research, I try to bring these two closer to each other. I try to use techniques and concepts developed in computer science to check complex specifications on top of differential equations or difference equations with continuous state spaces. So there is a need that these two communities come closer to each other with respect to the richness of the class of the specifications and richness of the class of models they are interested in studying. In today's presentation, I will focus on one class of models, which are difference equations over continuous state spaces, influenced by uncertainty. So therefore, I focus on stochastic setting in this presentation. And I will show how we can use abstraction methods to study properties of these models. Okay, so this slide shows the high-level idea of how the abstraction can work for formal verification. Suppose we are given a complex model here together with a specification, or we may have a cost function, a reward function that we want to optimize. Since the model is complex, we cannot solve the problem analytically. We have to use approximation methods. So we replace the complex model with a simple model. We also replace the specification with another specification here called epsilon specification. And this epsilon shows the level of simplification. So we simplify the complex model to an abstract simple model. With respect to this epsilon, we also change the specification with respect to this epsilon. Once we have this simple model, we can use techniques from model checking to do automatic verification, or we can synthesize a policy to answer the question whether the epsilon specification holds or not, or whether the policy satisfies the policy when applied to the system satisfies the epsilon specification or not. But the answer of this question is over the simple model. We have to refine back the results over the concrete model. So we have to have a refinement mechanism that tells us how the answer of this question can be used to answer the same question over the complex model. If the answer is yes, we are lucky and we can stop. Otherwise, we have to go back and change epsilon here use another simpler model with another epsilon specification, and do the whole procedure again. So it's a sound procedure, but it's not complete. So in today's presentation, I will discuss stochastic difference equations. And here for the simple model, I will discuss two candidates. One is Markov chains, and the other one is dynamic Bayesian networks. And I discuss how this epsilon can be quantified when we simplify and abstract the model. Okay, so with this introduction, this is the outline of the presentation. First, I will give some preliminaries on Markov processes and safety specifications. Then I will discuss Markov chain abstractions. And then I show how the dynamic Bayesian networks can be used as abstractions of Markov processes. And finally, I will end the presentation with some concluding remarks. Okay, so let's get started. So the best framework for a study discrete time stochastic systems is Markov processes. So you have a process, you have a system or a process that changes over time, but in discrete time. So the time is discrete. So you have time equal to 0, 1, 2, and so on. And at each point in time, the state can take some value. So you have a state space S, and then for the evolution of the system, of the process from one state to another one, we have a transition kernel. So this transition kernel gives you the probability of jumping from one state to a subset of the state space. So you have the current state of the system. Here you see ST, the current state of the system is S, and the next state of the system could be anywhere in the state space. And the probability of jumping to subsets of the state space is given by this transition kernel, which is denoted by capital T S. Yeah. So one major difference between finite state and continuous state spaces is that we can't assign probability to all subsets of the state space. We need to define a sigma algebra, let's say a Borel sigma algebra, that gives us the set of subsets of the state space where we can assign probability to. And this transition kernel is defined only on the elements of the Borel sigma algebra. Another point that I want to emphasize is that usually these transition kernels are specified by density functions. And these density functions, when you integrate them, you obtain the probability associated to each subset. Okay, so to make it a bit more visible, assume that the state space is two-dimensional Euclidean domain. So you have the current state S. For any subset of the state space, any measurable subset of the state space, you have the probability of jumping to in the next time step, and the probability is given by the transition kernel. And if you have a density function, you integrate the density function over the set C to obtain the probability associated to that set. If we want to compare this with the finite state space, in finite state space, we have a Markov chain. So in Markov chain, we have a finite number of states, A, B, and C, and we have probabilities of jumping from one state to another one. So for example, here, probability of jumping from a state A to a state B is given by P12 written here. So here it's easy. We can have all these probabilities of jumping from one state to another and put all of them in a matrix. And this matrix fully characterizes the probabilistic evolution of the system. But in the continuous state space, we need a transition kernel. We cannot assign probability to points in the state space, to elements of the state space, but we have to assign probability to subsets of the state space. So you can think of Markov processes as an extension of Markov chains over continuous spaces. So there is a theorem proved by Kallenberg in 1997 that shows a connection between Markov processes and dynamical systems. And the theorem says that if we have a Markov process with the transition kernel that I just described, we can have such a dynamical representation that the next state of the system is a function of the current state and some noise. And this noise is a random sequence with known distribution. And these are independent, identically distributed. So if you have such a representation, you can construct a Markov process with a transition kernel. And if you have a transition kernel, you can transform that transition kernel to such a representation. Yeah, and you get the distribution of the noise together with this vector field f here for the dynamical system. So usually, if you look at the control theory, they tend to work with this equation rather than the Markov process and the transition kernel. But if you want to study the probabilistic behavior of the system and probability of satisfying specifications over paths of the system, it's better to use the Markov process representation than the dynamical representation. To make it a bit more concrete, I give here an example, which is a linear dynamical system, n-dimensional linear system. So the next state is just a matrix times the current state and a vector for the noise. If we assume that the noise is Gaussian, so this is the Gaussian noise with some mean vector b and some covariance matrix sigma, we can easily construct the density function of the system, and the density function becomes Gaussian because the density function is conditioned on the current state. Once you know the current state, this term is just a constant vector, and you add it to a Gaussian random variable. It becomes again a Gaussian random variable, and this is the formula for the density function of a Gaussian random variable. You just need to specify the mean and covariance matrix. The covariance matrix is the same as the covariance matrix of the noise, and the mean is this term phi times s plus b. So it becomes this term, the constant term, and the mean of the noise here. Yeah. Just to show you how this density function can be constructed from the dynamical system. Okay, so now let's look at a simple specification like safety. So in safety, we are asking about the probability that the paths of the system stays in the safe set A during a time horizon. So the time horizon here is fixed. So from the time ranges from 0 until capital N. And we want to compute the probability that the system starting from the initial condition S0 remains inside the set A during the time horizon N. And so this probability is a function of the initial state. It also depends on the safe set A here. And it has applications in many domains. For example, power networks, if you don't want to have blackouts. So it's more like a safety specification in systems biology, in air traffic management, in risk analysis, robotic surgery, and so on. So in all of these application domains, we require safety of the system. And safety means we want to keep the states of the system within some safe range. Now let's see how we can characterize this probability, the probability of safety. We can use a Bellman equation or Bellman recursion to characterize the safety. So this safety can be seen as expectation of the product of these indicator functions. So the indicator function decides whether the state is inside the safe set or not. So this indicator function of A of S0 is 1 if S0 is inside A and is 0 otherwise. So if we want to keep the trajectory, the path of the system to be safe, we have to check whether all of the states are inside the safe set. So we take these indicator functions and we take the product of them. So if the product is equal to 1, it means all of the states have been inside the safe set. If it's 0, it means at least one of them is going outside of the safe set. And if we take the expectation of this Bernoulli random variable. It's Bernoulli because it takes values 0 or 1. There's no other option. And we just want to compute the probability that the random variable is equal to 1. It's expectation of the Bernoulli random variable. And it gives us the probability of safety here. So this is a way of characterizing safety using expectation. So these are the data we start from with. We have the safe set, we have the density function, and we have the time horizon. To compute this expectation recursively, we define some value functions. So these value functions Vk map the whole state space to the interval 0 and 1. And these are connected together recursively. From Vk plus 1, we can construct Vk. And this is more like taking the expectation. So you multiply Vk plus 1 with the density function, integrate over the whole state space, and multiply it again by the indicator function of A. And the initial function is also the indicator function. So to give you some intuition on how this recursion is obtained, so it's more like taking this expectation backward. So we first take the expectation of the last element, we compute it, and then we take the expectation with respect to the previous state and so on. So it's more like making condition on the history of the path and taking the expectation with respect to the states in the past one after another. So we start from this indicator function here. You see here, this is Vn. And then for the previous one, we somehow take the expectation, including the previous indicator function. And this is the previous indicator function, and this is the expectation operator. So this is a way of characterizing this, and the output of the output of this procedure would be the value function V0, which gives us exactly the safety probability. Now, the problem is that there is no analytical solution in general because of the continuous nature of the state space, and we have to approximate the solution with explicit error bounds in order to be able to judge safety of the system. So now let's see how we can use Markov chain abstraction to simplify the model and check safety. Okay. So this slide shows how the Markov chain abstraction works. So we are given the safe set A. We partition the safe set into smaller sets, here denoted by A1, A2, A3, and so on. These are partition sets of A. Then we pick representative points. For each partition set, we pick one point inside that set. For example, for A7, I pick V7 here. For A5, I pick V5, and so on. I also assign a dummy state here for the rest of the state space. So only partitioning the safe set and replacing all the states outside of the safe set with a dummy state here. So these representative points together with phi form the discrete state space of the Markov chain. The next step is to compute marginals, the probability of jumping from one state to another one. For example, if I want to compute the probability of jumping from V7 to V5, I take the integration of the density function initialized at V7, conditioned at V7, and then the integration over A5. So I have to do it for all the pairs of discrete states. For any pair of states, I compute one integral to get the transition probability or marginals. And finally, I compute safety over the discrete space over the Markov chain, where all the points inside the safe set, these representative points inside the safe set, these are safe, but this dummy state is unsafe. So to quantify the error, we need an assumption. The density function, if we assume that the density function is Lipschitz continuous, we can find the error, an upper bound for the error. So this continuity is more like saying that if I change the condition S, the condition S to S prime, the changes in the density function is somehow upper bounded by a linear term. So it's just a constant H times the changes in the current. And again, to give you some intuition on why do we need this assumption, when we do the abstraction here, we somehow replace all the points inside a partition set with only one point. So we are making error here. We somehow lock all the states here in one point. That's why we should be able to make sure that the changes because of the state inside one partition set is not that much. And this is exactly quantified by the Lipschitz, which gives us a bound on the error we make when we replace a state S by a state S prime. Yeah. And if we have an assumption, we can have formal error bounds for we can have formal errors for the abstraction. So this is the solution of the safety over the original model, and this is the solution of the safety over the abstract model, and the error is bounded by this term. So it's bounded by the horizon of the specification, it's bounded by the size of the safe set here. A bigger safe set, it means bigger error. It is also proportional to the Lipschitz constant, and this delta is the diameter of the partition, and this is exactly what we can control. So this delta shows the size of the partition set. So if we want to reduce the error, we simply select a smaller partition set, which increases the size of the abstract Markov chains. And this helps us to partition the safe set uniformly. So for a given error, let's say if you want to have the error to be 0.05, you put this quantity equal to 0.05, and then you pick the related delta. And with respect to this delta, you put a grid on the state space. So you can use, for example, hypercubes with this delta, with the size of this delta, and then you get the status of the Markov chain. I have worked on extensions of this technique using adaptive and sequential grading procedures. Instead of partitioning uniformly, you can try to select partition sets with different sizes depending on the local behavior of the system. I have done some work on relaxing this continuity assumption. If the continuity assumption does not hold, we can still quantify the error. I have also developed some techniques for having higher order approximations because now the error that I showed you depends on delta. There are also some other techniques. You can have powers of delta, like delta to the power 2, delta to the power 3, and so on. So this helps us to improve the computational complexity of the approach. Another technique I have developed is that instead of solving the problem backward in time, we can also solve it forward in time. And that depends on the nature of the system, of the dynamics of the system, whether they are contractive or they are diverging. Depending on the dynamics of the system, one of these computations could be better than the other one. And if we want to do synthesis, there are also some results I have published that we can do synthesis, find a policy to maximize the safety probability. And all these techniques have been implemented in a software tool, FAUST2, which receives the model of the system, the specification, and you pick which method you want to use to solve the problem. It gives you the Markov chain abstraction that you can export to other tools like Prism or MRMC. And do verification and synthesis in the discrete domain there. It can also give you the probability of safety and reachability and show the probabilities for lower dimensional systems. Okay, so this was the first part of the presentation on showing how Markov chain abstraction can be used. Now in the second part of the presentation, I will discuss abstraction, use dynamic Bayesian networks, and this is useful when we have a kind of a structure on the dynamical system. Okay, so I will give a pause and then I will start recording again. Okay, so in this slide, you can see the same dynamical representation, but written explicitly. So instead of having one equation in n-dimensional state space, I have written down n equations, each one specifying the evolution of one of the states, one of the state coordinates. So instead of a vector, you have S1, S2 until Sn. The next value for S1 is a function of the current states, S1, S2 until Sn, and it's also influenced by the noise. So here, the only assumption I put here is that the noise affecting these states are independent. So Xi1, Xi2, and so on, affecting the noise, affecting the states are independent. So S1 is influenced by Xi1, S2 is influenced by Xi2, and so on. And you have the independence assumption for these noises. So if we have this independence assumption, then we get a nice structure for the conditional density function, which becomes like a product form. So the conditional density function becomes the product of n individual density functions, each one for one of these equations. So related to the first equation, we get this density function T1, which gives the distribution over S1 bar over the next state of S1 conditioned on the whole state vector at the current time step. The same thing, we get another term for S2, another term for S3, and so on. So this product structure helps us to have a more efficient way of computing the safety probability, and it also helps us to take a sparsity of the dynamics into account, to take into account the structure of the dynamics and how they are influencing each other. Okay. And this shows a nice example that this structure is already there. It's part of the system itself. So think of the system of mass spring damper. So you have n masses, m1, m2, m3 until mn, and these are connected together with springs and dampers. And as you can see, for example, M2 is influenced by only the neighboring masses through this spring and damper here, and this spring and damper here. It's indirectly influenced by the other masses, but the direct influence is coming only by two of these masses. So there is a structure there. And if we write down the equations for the movement of these masses, we can have a linear dynamical system, and this state matrix phi becomes a banded matrix. So you have the diagonal elements to be non-zero, and some of the off-diagonal elements are non-zero. The rests are all zero. So we get a structure in the dynamical equation. And the same thing if you have a large-scale interconnected systems, with lots of subsystems connected together. So as you can see here, this equation is only for one of these subsystems, which is influenced by only the neighboring subsystems. And usually the number of neighboring subsystems is substantially smaller than the total number of subsystems in the whole network. And this structure appears in many application domains like traffic systems, smart power networks, sensor actuator networks, and so on. So you have a large number of interacting components, and each component is interacting with a very small subset of other components. To give another example, consider a metabolic network. So here we have some extracellular metabolites, A external and E external, and some intracellular metabolites, A, B, C, D, and E. If we write down the dynamics for metabolites concentrations, we get a differential equation, stochastic differential equation. And usually there is a stoichiometric matrix in this equation that gives exactly the structure, the way these metabolites are influencing each other. For example, here B is connected to A, E, and C, and this connection is represented into, is reflected into this stoichiometric matrix. So all I want to say is that there is a structure, and we have to use this structure to make our approach more efficient. So to capture this structure, we can use dynamic Bayesian networks. Here in this slide, I will give a very a simple explanation about Bayesian networks to have everyone on board. So for Bayesian networks, we have a set of nodes here. For example, think of an exam and the grade, the mark of a student for different exams. So the grade of a student depends on the difficulty of the exam and also the intelligence of the student. So these are the two factors affecting the grade of the student. And at the same time, we have also some exams that are standard and they are somehow tuned to assess only the intelligence of the student, and the result of such an exam is independent of the level of difficulty. So it's a standard to measure the intelligence. And for example, if someone, as a student, wants to get a recommendation letter from the supervisor, the recommendation letter is usually depend on the grade of the student. So here we have some qualitative information on how these variables are influencing each other directly and how they are independent of each other. So these arrows reflects dependency. And if there is no arrow from one variable to another one, means they are independent. So this is the qualitative information captured in Bayesian network. And also we have quantitative information. And this quantitative information is in the form of conditional probability tables, so which assigns probability to different values of each variable, conditioned on values of previous or parent nodes. For example, here the grade has three possible outcomes: low, medium, high, and each one has its own probability depending on the difficulty of the exam. So here the difficulty is taking two possibilities indicated by I0 and I1, and it also depends on the intelligence of the student, which is denoted by two possibilities, D0 and D1. So that's why we have a 4 by 3 table, which gives us these conditional probabilities. The same thing for this node, the same thing for this node. So for each node, we have these conditional probabilities, probability tables. And also for the leaf node, we also have, for the initial nodes, difficulty and intelligence, we also have some tables which assign probabilities to different possibilities of these values. Yeah. So summarizing, we have two types of information. Qualitative, which indicates the dependence or independence, and quantitative, which gives us conditional probabilities for these variables. Now, the Bayesian network by itself doesn't have time in it. If we encode the time, it becomes dynamic Bayesian network and it changes over time. So in each time slice, we have a Bayesian network. So this is the Bayesian network at time slice t. This is the Bayesian network at time slice t plus 1. And we also have to show how the random variables in each time slice are connected together. Okay, so, and this B0 is indicates the Bayesian network at time slice 0. Just a generalization of Bayesian network to encode time. Okay, so now here I will discuss how a Markov process can be represented by a dynamic Bayesian network, but with continuous variables. Again, consider the linear dynamical system in 4-dimensional Euclidean domain, and suppose the state matrix phi has this kind of structure. So most of these elements are 0, only the diagonal elements and the ones right below the diagonal elements, these are non-zero. So we can encode such a Markov process with a Debian. So this is the time slice, the Bayesian network at time slice t. It has two set of variables, S1, S2 until S4, which is related to the current state of the system, and we have the bar version, which is related to the next state of the system. And we have some arrows connecting these the current states to the next states, and this connection is through the conditional density function. So you can see, for example, we know that S1 only depends on itself, so that's why we have an arrow from S1 to S1 bar. If we look at the second row of the matrix, S2 depends on S1 and S2. So that's why S2 bar is connected to S1 and S2. So there are two arrows from S1 and S2 to S2 bar, and so on. So the structure of this matrix and how the states are dependent is reflected in this dynamic in the Bayesian network at time slice t. Now, the same structure appears at time slice t plus 1, and we directly connect S1 bar, S2 bar, and so on to S1, S2, S3, and so on in the next time slice. So these blue arrows shows how we go from time slice t to time slice t plus 1. And here the main issue is that these random variables are still continuous. They have a continuous state space. The real line is their domain, and we have continuous density functions. It's not discrete yet. So what we can do is to approximate it with a discrete version. So we keep exactly the same structure, but we replace continuous variables with discrete variables. And instead of density functions, conditional density functions, we get conditional probability tables. So these becomes tables, but these are continuous functions. And now I want to discuss how this discretization works, how we can go from these conditional continuous density functions to tables. Okay, so I give this construction over the two-dimensional domain just for visualization. So, but the approach is general. So suppose you have two states, S1 and S2, and you have a safe set A, which is not aligned with the coordinates. So what we do, we start by first projecting the safe set A along each coordinate, along each axis, to get two sets here, D1 and D2. Then we partition D1 and into D2 into smaller partition sets, and then we pick representative points. So here you have these representative points here, and also one dummy state for the outside of D1. The same thing we do it for D2. We pick these representative points for partition sets inside D2, and we pick a dummy variable for outside of D2. So these dummy variables, these representative points, and the dummy state becomes the state space, the finite state space of the random variables in the DDN. And the conditional probability tables, they are also constructed by integrating these density functions. So similar to what we had in the Markov chain, we take the density function, we integrate the density function over the partition set associated with the representative points, and this is conditioned on the value of the random variables in the parent nodes. And we also make all these dummy variables to be absorbed. So it's very similar to Markov chain abstraction, but it's done for each coordinate, each axis independent. Yeah? And the output becomes a DBN with discrete random variables. So the safe set, we also need to approximate the safe set because it's not aligned with the axis. We somehow over approximate the safe set with a union of these hypercubes here. So if we take the product of all these partition sets, it gives us a partition for the whole state space, and we take the union of some of these partition sets for the whole state space to cover the actual safe set. So in this case, we are making some error. The first error is related to the discretization, and the second error is related to over approximating the safe set. Now, let's first see how the computation can be done once we have the discrete domain. So you recall the Bellman recursion for the Markov chain when we for the Markov process when we wanted to compute the safety. Now in the discrete domain we have a similar equation, But instead of integration, we have summation. So the integration is replaced by the summation. And we also replace this density function with the product of these conditional tables. So you have a bunch of conditional tables, you have to take the product of these conditional tables, and then you have to take the summation over some of the variables. And this is studied extensively in the literature, and there are efficient methods on how to compute this sum product expression. For example, I give you some intuition. There is a factor graph that shows the connection between these tables and the variables. And usually, because of this type of dependencies, we have loops in the factor graph. There are methods on how to combine the variables and the tables to eliminate the loops and have a tree called a spanning tree. And then we have a kind of optimal way of taking the product first and then sequentially taking the summation over the variables to make the approach more efficient. There are also some approximation algorithms on how to approximate the solution, for example, message passing and so on. So I don't go into the details, but just wanted to clarify that once we have this in the discrete domain, there are efficient methods on performing the computation in the discrete domain. Now let's go back to the major challenge of quantifying the error. Here again, we put an assumption on the continuity of the density functions. We assume that all these individual density functions are Lipschitz continuous if we change the current state S to another state S prime by only changing one of the coordinates. So all the other coordinates are the same. I only change Si to Si prime. So the rest of the coordinates of the current state are the same. Then we get a kind of a bound on the changes in this density function. And here the constant is denoted by Hij. So is related to the coordinates I'm changing, and J is related to the index of the density function. So if I have such a continuity assumption, we can quantify the error, and this is the error which gives a bound on the difference between the safety probability on the original model and the safety probability computed over the discrete deviant. As I mentioned before, there are two contributions in the error. One contribution is related to the over-approximation of the safe set. So it's proportional to the volume of the over-approximation. You see this term is the volume of the difference between the over-approximated safe set and the actual safe set. It's also proportional to the horizon of the specification and an upper bound on the density function. Yeah. And the second term is related to the discretization. It's proportional to the horizon of the specification. It's somehow related to these Lipschitz constants, the size of the projection of the safe set, and also the size of the discretization. And this is the term we can control. To reduce the total error, we can reduce the size of the partition sets as much as we want. And this also leads to reduction to the over-approximation of the safe set. So we can tune both contributions of the error with this discretization parameter, and then get any bound on the error. So the approach can be made precise as much as we want, and the cost we pay is related to the size of the discrete deviant. So if you want a very high precision, these conditional tables become larger and larger, and the computational complexity increases. So comparing to the Markov chain abstraction error, we have contributions for each axis independently. So for each axis, we can select different error, different discretization parameter, and we get the summation over this delta I. But here we had only one delta related to the grid we put on the whole steady space. Okay, so just to give you a comparison on these two techniques, the Markov chain abstraction and the DBA, I just give formulas on the error for this linear system. Suppose you have the linear system and you have a safe set in the shape of a hypercube. So this minus alpha and alpha shows the boundaries of the safe set in each dimension. And the abstraction error is bounded by these two terms. So the first thing, term I want you to notice is this red part. So in the DBN, you have n times eta, and here you have eta to the power n. So this shows that the error of the Markov chain abstraction increases with respect to the dimension of the system exponentially, but here we have linear increase with respect to the dimension. So n is the dimension of the system. So if you have a large dimension, a large dimensional system with a specific structure, it's better to use the DBN approach because the error increases linearly with respect to the dimension. Another term I want you to notice is this blue part, which is the norm of the the state matrix. So this blue part for the DBN is bounded by is proportional to with respect to the sparsity of the state matrix phi. But here the Markov chain is proportional to the square root of R, which is the sparsity factor. So if you have a sparse dynamical system, this sparsity is reflected in the computations much better if we use the DBN. So here we have R itself, but here we have the square root of R. And to just show the values, the numbers, if I want to compute the marginals, the number of transition probabilities for the Markov chain, you see here the exponent of 10 increases. So you have some exponential growth in the number of marginals I have to compute. But in the DBN, I have a kind of linear growth in the number of marginals I need to compute. Okay, I think this brings me to the last slide. So I discussed how we can use abstraction as a method for safety, for checking safety. We can use Markov chains and dynamic Bayesian networks with finite state spaces. We can use the structure of the dynamic and use Bayesian dynamic networks. We have guarantee formal error bounds under suitable continuity assumptions. In general, currently I'm working on how to use data to check a specification on dynamical systems. I'm working on extensions of these techniques to infinite horizon specifications like Buki specifications, GR1 or omega regular specifications. And I have some already some results published or under submission. There are also some directions on using discretization-free approaches. And it's for example, approaches that don't need discretizing the state space. Another direction is how to solve games over continuous spaces. And if we have interacting dynamical systems, a large number of them, how we can synthesize policy by broadcasting a unified signal to all of them. So thanks for listening to this presentation. Since it's a recap, there's no opportunity to answer questions now, but get in touch if you have any questions. Thank you very much.